this video of torsion. In the last class, last video, we derived the torsion equation, general torsion equation, which is given here. Now let us look into the analysis of this equation, how to solve numerical problems using this equation. So for solving a numerical problem, we can use any two, the combination of any two of this equation. So first, let me take these two terms, the first two terms together. So that is given here. Now it is given that T by J is equal to tau by R. Now T already we know it is the twisting moment, J is the polar moment of inertia, and tau is the shear stress developed at a radial distance of R from the longitudinal axis. R is a radial distance from longitudinal axis. So if we need to find the stress at this point, we have to measure the radial distance of this point from this end. And once you put in this equation, you will get the stress at this. Similarly, if you need to find the shear stress at this point, you need to find here the radial distance is nothing but the radius itself. So my point is R is not the radius, R is the radial distance. R can range, the value of R can range from 0 to capital R, the radius. If it is at the center, it is 0. From this equation, it is obvious that when R is equal to 0, tau is 0. That is at the center, the shear stress due to torsion is 0. And it will be maximum at capital R, that is the radius and the circumference will be the maximum. So I can sum up that the shear stress will be 0 at the center and maximum at the periphery or the circumference. That means it will go on increasing from 0 to a maximum of R, maximum value at capital R at the radius. So this is how a stress profile looks. You can see here. This is the value of shear stress here. A radial line is shown here. The value of shear stress at this point is 0. It goes on increasing, and at this point, the value of shear stress is maximum. It is given as tau max. So that is the stress profile in a cross section due to torsion. In a cross section, any radial line you draw, I can draw another radial line like this. Then I can draw the stress profile like this. This is the stress profile. You can mark the arrows here. Any radial line you draw, the stress profile looks like this. It will be 0 at the center and maximum at the circumference. Or I can draw a vertical line also. I can draw a vertical line. Here also it remains the linear profile. This is the shear stress. And goes on as such. So that is the shear stress on any radial line. As you move away from the center, the shear stress value of the shear stress increases. So that is what is this equation is showing us. Now for a circular cross section, I have already told you in the last video, J is polar moment of inertia is 5 d raised to 4 by 32. So you can write this form, tau is 32t by 5 d raised to 4 into small r. Now, I have already established that tau max occurs at the radius, that is the circumference when small r is equal to capital R. Then I can write, and also I have written here R is equal to capital D by 2. Capital D is the diameter of the cross section, capital D by 2. So when I substitute D by 2 for capital R, then d raised to 4, 1d out of the d raised to 4, and this d get cancelled, and 32 and 2 get cancelled. The final equation, tau max equation, the maximum stress equation becomes 16t by 5dt. So this is an important equation for a circular cross section. This is an important equation. We will be asked about what is the maximum when you are applying a twisting moment of this much twisting moment, what is the maximum shear stress value that is developed in the material. Or it can be asked in the reverse manner also. That is, the maximum values tau max will be given. The maximum possible stress that the material is able to sustain is this much. Then what is the twisting moment, maximum twisting moment that we can apply at that section? So then you will have to find from tau max, you will have to find T, the twisting moment value. So this equation can be asked in any manner, means forward calculation or reverse calculation. All you need to know is the diameter. So that is one form of the equation. That is one application of the torsion equation. Now for hollow circular section, the capital J value is pi dO raised to 4 by minus di raised to 4, where dO is the outer diameter and dA is the inner diameter. dO is the outer diameter and dA is the inner diameter to the center. So if I am to calculate if I am to show the stress profile here, it will be like this. It will be like this. That is, it will be 0 at the center, but center there is no material. The material starts only at the inner diameter, but we can then continue from there. There will be no 0 here. There will be no position of 0 stress here. It will continue towards the so that part of the triangle will be missing. The other things remain same. So tau max calculation is like this, and you substitute dO by 2. Okay, outer diameter by 2. Here then there is a simplification here. It is to assuming K is the ratio of di by du. That is inner diameter to outer diameter. If K is the ratio, I can take the dO raised to 4 outside and I can write K raised to 4. I will substitute 1 here. dO raised to 4 is taken out. Then this becomes di by dO raised to 4. di by dO raised to 4. And then I can substitute that as K raised to 4. That is what is written here. That is K raised to 4. So then dO and dO raised to 4, which is taken out, is cancelled. Similarly, 2 and 32 are get cancelled. So the final equation boils down to 16T by pi dO cube, which is this much is same, almost same as the solid circular section. Solid circular section. But here one more term comes, that is 1 minus K raised to 4, where K is the ratio of inner diameter to outer diameter. And K value will always be less than 1. So this is the equation for hollow circular section. So mostly, in most cases, you will be quizzed on, the question will be based on a circular section or a hollow circular section. So now at this point, you will be able to handle the stress values of both torsion and both hollow circular and solid circular sections. Now the second case from the equation is T by J equal to G theta by L. I have taken the from the general equation, I have taken the first term and the third term. And in this case, T by J is equal to G theta by L. I can rearrange this equation to write as T by theta equal to Gj by L. T by theta is nothing but load by deformation. Load by deformation. In case of spring and all, you might have studied about force by displacement, or force by elongation. That is nothing but K. That is spring stiffness. So every material is equivalent to a spring. Every material can be considered, elastic material can be considered equivalent to spring. So this equation was in case for a linear material, inner material, but in this case it is a torsion, the load by deformation. Here the deformation is theta and load is twisting moment. And I must remind you that whenever you apply theta in this equation, it is in radians, not in angles. It will be in radians. You will have to apply all theta values in radians. Except when theta comes along with sine or cos, you will have to apply it in radians. So T by theta is Gj by L. So Gj by L is also a form of torsional stiffness. Then theta. Theta can be written as another form of the equation. Theta can be rearranged to be written as TL by Gj. And G and J are respectively the rigidity modulus, and J is the polar moment of inertia, T is the twisting moment applied. L is the distance, the length between any two cross section 1 and 2. Where theta is the part here is does not come into the PDF. Theta is nothing but the relative rotation between the cross sections at theta 1 and theta 2. The relative rotation theta 1 minus theta 2. The modulus of theta 1 minus theta 2. How much 2 is rotating relative to 1, or how much 1 is rotating relative to 2. That is what is shown here. Theta is theta 1 minus theta 2, and L is the distance between 1 and 2. So I can say that theta is the angle of rotation of relative angle of rotation of two sections at a length of L between them. So here I have assumed the two sections to be 1 and 2. Assume the two sections to be 1 and 2, and the length between them is L. Now, if one if one end is fixed, and we need to find the rotation of the free end, then I can substitute the total length here. Here, one end is fixed. Now I need to find the rotation at the free end. This will be the maximum rotation. Because in the first video, I have already said that all the cross sections will be rotating at some angle between 0 and theta, and this face rotate by 0 and this face rotate by theta. Now to calculate theta. Now the distance between this and this is nothing but the fixed section, and free section is free face is the total length L. So I can write theta is equal to TL by dj. This will be the maximum rotation. This will be the theta max. Okay, theta max will be this much. This is the theta max. So to calculate the maximum angle of rotation, we will have to use the total length. Otherwise, that may not be the total length. It will be only some value of length between two cross sections. So maximum value of length is this much. Then when you substitute based on this equations also, you can be asked question, that is the maximum value of rotation of a cross section is to be minimized to 2 degrees or 3 degrees. Then you will have to convert that 3-degree value into radians. Then you will have to substitute in the equation, and what is the maximum twisting moment that can be applied. Now this can be given, and you may be required to find the t value, or else t value will be given. The twisting moment this much is applied, length is this much, and g is g value, j value, this all given. If t is given, you will be asked to find the value of theta, the maximum rotation. This way also questions can be asked. Thank you.